one other thing. Now this takes a little bit more time, but this is now leading us into the rest of this week, what we're talking about. And that's this concept of block entry in sequential multiple regression. Now, notice I'm saying sequential because it's, well, in simultaneous regression, everything's a block. We enter all the variables together in one big block. In sequential multiple regression, you can do that kind of bit in pieces. You might enter a set of variables in one step and then add more variables beyond that, based on your causal model. Often why you might see this is that you've got two variables that are related somehow. You know they're related, but there may really be a very poor reason to say one causes the other. Because notice, so far when we did sequential, we only had arrows. Everything was a one-headed arrow. Everything caused something else. We didn't have those, well, they're correlated. I don't really know what the relationship is. But sometimes you might, in which case it makes sense to enter them as a block. We're going to get to, again, the other more general reason why it makes sense to enter things in a block in a few more minutes. But for example, kind of an example of the first is, let's say I'm looking at, instead of mom's education, I'm looking at mother's and father's education. Now here might be a case, notice you've got those two variables, and we're not sure. I mean, does mom's education lead to higher father's education? Does higher father's education lead to higher mother's education? They're probably both related to something else, you know, in terms of their combined, they met in school, or they met, you know, whatever it is that leads those two to be correlated. But we're not going to try to say, we're not going to draw an arrow saying mom's education leads to dad's education, or the other way around. We're just going to say they're correlated with each other. And I'm going to treat them as a set. We're going to call that set parent education. And now it'll be parent education. It'll be two variables that comprise mom's and dad's education. And we're going to analyze them and to a large degree interpret them as a set. It's pretty straightforward once you do it. The Model 1, instead of just entering mom's education, we enter mother and father education. So we enter the two of them as a set together in Model 1. Notice the degrees of freedom change a little bit, because now we used to have 1 because it was one variable. Now we're adding 2, so it's 2 and 397 degrees of freedom because we have two variables. Otherwise, we interpret it exactly the same way. It's calculated exactly the same way. You know, the sum of squares is the same. We add up these to get the sum of squares. You divide this by this to get that. You divide this by this to get that. You divide that over that to get that. It all works out the same. Nothing's fundamentally changed, other than we're putting in two variables together. And now our f is with 2 and 397 degrees of freedom. F is 30.989. P is less than 0.001. So that's good. The mom and dad education as a set accounts for 13.5% of the variance. You know, 0.135 is our R squared. So 13.5% of the variance as a set. The R squared change formula is exactly the same. You just need to keep track of K nu now is 2, because we've added two variables. You just have to plug in the right number of variables when you're adding in sets. It's not one variable anymore. So we do the calculations for the F change, and you can see, I won't walk everybody through it, but we get the exact same number, which we know for the first model. It'll be the same R squared change. So everything worked. The degrees of freedom are still n minus 2, you know, the K new minus K old, n minus K minus 1, right? So it's the same degrees of freedom. P is less than 0.001. So everything, you know, just like we just were doing. Then after we enter so we first enter mom and dad's education, then we enter school quality. School quality accounts for an additional 1.5% of the variance. We do we can do the F change test again, right? So now it's going to be the 1.5 minus 0.35 the r squared new 1.15 r squared new 0.15 r squared old is 0.135 divided by k new. How many variables? 3. Minus k old, the old was 2, so 3 minus 2, divided by 1 minus the r squared new, 0.15, divided by n minus k new, 3 minus 1, gives us 7.101. Everything works. That just tells us that adding school quality had a statistically significant effect. It accounted for an additional 1.5% of the variance. Right, looking at this. It's unfortunate those are kind of an order of magnitude different. This is how much additional variance school quality accounted for. This is the total of school quality and mother's education, and mother's and father's education. Right? This is the change. This is what school quality added. Right? And then, again, kind of at the bottom, when we add study hours, the r squared is now 0.156. The change in r squared is 0.006. So the r squared new is 0.156 minus the r squared old is 0.150. K new is now 4 variables. Minus k old is 3, divided by 1 minus r squared new, 0.156, divided by n minus k new minus 1. 400 minus 4 minus 1 gives us an F of 2.687. The degrees of freedom are 1 and 395. P is 0.102, so that's not significant at all. That didn't add anything. Visually, we can draw a Venn diagram just like before, except now notice education. We don't just have mom's education. We don't have a circle for mom's education and a circle for dad's, because we entered them as a block. We entered them as a set. So we have one big circle that is parent education. And that's 13.5% of the variance, 0.135. I meant to change the colors, but I forgot to make it a little lighter. But it shows up on the slides, right? So that's 0.135. School quality is 0.015. And study hours was at 0.006. So again, it all adds up sequentially just like before. We can add them all up. It all makes sense. We're just talking about mom's and dad's education as a combined concept. We're not talking mom education. We're not talking dad education. We can a little bit, and we'll get to that later. But the focus is we've got this new idea, this new concept called parent education, or new construct, parent education, which is made up of 2 variables. Here's our regression model, our unstandardized regression coefficients, the t-test for each of those. It's the t-test. Here's our test for the effect of every variable, controlling for every other variable. So in the end, we see in the final model, mom's education is statistically significant, controlling for everything else. Dad's education is not. Its p-value is 0.636. The t-score was negative the t-score for, well, actually, what was our degrees of freedom in the end? 395, right? So we have to go to that degrees of freedom for model 3. So our t-score for mom's education with 395 degrees of freedom is 5.650. P is less than 0.001. So mom's has a unique effect controlling for all the other variables. Think of the little path diagrams. That's that effect that mom's education has straight to grades. The unique effect of father's education is 0.636. I'm sorry, well, the unique effect of father's education is negative 0.009, right? It's the regression coefficient. The T with 395 degrees of freedom is negative 0.474 for a p-value of 0.636. That's not significant. That's that unique effect of the father variable controlling for everything else. School quality has a unique effect of 0.042. T with 395 degrees of freedom is 2.471. P is 0.014, so that is statistically significant. And again, that's the effect of school quality controlling for everything else. And we've already belabored it. Study hours we saw was not. Now, while we have talked about mom's education and dad's education as this parental education construct, this blob construct, it's just parent education. You can, as we're kind of implied when I just went through those regression coefficients, you can still kind of look at the individual effect of each. And we see that even though we treated them as the same thing, think back to basketball. And you can kind of think of them as a team. We treated them as a team. But in this case, mom's education is the Shaquille O'Neal of that relationship. That's very significant. The effect of dad's was not. Dad's education uniquely did not have an effect. Mom's education uniquely did have an effect. You can actually measure how big those are by squaring the part correlations. Remember, we talked about each of these part correlations squared is the unique variance for that variable controlling for everything else. From the Venn diagram, square each of those values, and that's that little piece of the Venn diagram that is only owned by that variable. So, if we square mom's education, well, we saw the total R squared was 0.135 for parent education. If we take mom's as 0.258, mom's part correlation was 0.258. We square it, 0.258 squared is 0.067. So about 6.7% of the variance in grades is related just to mom, controlling for everything else. Dad's is negative 0.022 squared is 0.0005, very small. And the total of them combined was 13.5%. So about half of the parent education effect is uniquely mom. And then a tiny little bit is uniquely dad, and close to half is mom and dad together. It's kind of that overlapping. It's not unique to either of them. It's what they have in common. Higher educated parents, higher educated women tend to marry higher educated men, less educated women. That's just the way the world works. So it's that overlap. About half of that is, half of our parent education effect is not unique. It's kind of the two of them combined. But mom has a big unique effect all on her own. Moving along. So far when we've talked about sequential multiple regression, we've talked about there's that causal model. There are times when you will do a sequential multiple regression, even if there is no causal model. And reasons you might do that, and someone like Keith, he likes the simultaneous, but then immediately goes into where I'm entering some variables and then adding something. Reasons why you might do a sequential without a causal model, and it's where it's actually after telling you have to have a causal model, situations where it's okay are this whole slide I need to fiddle with, curvilinear effects. We'll see that in another 2 weeks. That you enter a group of variables and then let's test if there's a curvilinear effect. Or you're entering interaction, which we'll get to next week. We are entering a group of variables, and then I want to test an interaction on top of that. So there's situations where it is okay to do a sequential multiple regression without a causal model, because there's certain effects you want to test where you have to control for other things first. And you need to enter them as a set. So the only way to do it is a sequential. And it's kind of, I'm kind of getting a little bit ahead of us. But there's situations where you may need to enter a set of variables to see, is this set of variables significant? And that set might be a curvilinear effect, it might be an interaction effect. And the only way to test that as a set is to first enter all the other variables. And then I add this and look to see, is the R-squared change significant?
That's not fishing then?
That's not fishing. If you have a theory, well, people will fish for interactions all the time. But if you, to test, what was nice with the, notice with the with the test for the F change, for the R-squared change, it is a way of testing a group of variables altogether. The regression coefficients test is mom significant, is dad significant. It doesn't test is parent significant. We're going to see soon. For example, we can have a variable, are you black, Asian, Hispanic, white, whatever. And we'll have variables to test each of those, but those don't tell you, is there an ethnic difference? Treating variables as sets. Sometimes we have these sets for like race or ethnicity. And I want to look at that, if you want to treat it as, if you want to see, is this set significant, you have to first enter in all the other variables and then look at the change in R-squared. It's the only way to look at a set together, is that change in R-squared. You should still be driven by a theory, and you need to kind of make the analysis a little more complicated sometimes if you want to add something in the middle of your diagram. But we'll get to that. Kind of the key with this, and it's a little, I probably slipped this in a little too early. I should have waited till next week to come back. But being I've just been hammering home, sequential has to have a theory. Sequential has to have a theory. And then we're going to kind of slip away from that. And I wanted to point out that that's actually okay in situations, but maybe I should have.
No, just exception.
Yeah. And we'll see these exceptions. We're going to spend the next 2 weeks talking about some of these sorts of situations where an exception may come up. So again, it's kind of spelled out here. You need to use F change statistic sometimes to look at a group of variables. And the only way to do an F change is you have to have all the other variables in the model. So you have to sequentially add the ones I'm interested in, that set I'm interested in, sequentially after controlling for everything I wanted to control for. Again, and you can do that without a causal model. Okay, let's see. You know what? It's a little early. Why don't we take a break, and then we'll come back.